Now let's look at confidence intervals for the difference of means. So we still have our three conditions, random, 10%, and large counts. A college student wants to compare the cost of 1 and 2 bedroom apartments near campus. She collects the following data on monthly rent for a random sample of 10 apartments of each type. So we're looking at 1 bedroom and 2 bedroom apartments. Let mu sub 1 be the true mean monthly rent for all 1 bedroom apartments near campus, and mu sub 2 is the true mean monthly rent for all 2 bedroom apartments near campus. Check if the conditions for calculating a confidence interval for the difference in means are met. So we do have 2 random samples of 10 1-bedroom apartments and 10 2-bedroom apartments. We can't assume that 10 is less than 10% of all 1-bedroom or 2-bedroom apartments near campus. And it's not a large sample, and we don't know about the population distribution, so graphing the data that's given to us, the sample sizes are small, but the dot plots don't show any outliers or strong skewness, so we can move forward. So let's talk about the confidence interval. Remember, on your formula sheet, you have statistic plus or minus critical value times standard deviation of the statistic. So now we need to replace what the statistic is. That is the difference of the sampling means. Then, when we're looking at the standard deviation of the statistic, that is simply adding the variances and squaring them. But again, we're not going to have sigma. We're going to have the sample standard deviation. So remember, we're using standard error. So piecing that all together, you have your statistic, which is the difference of the means from the sampling that took place. You have your standard error, and then you have your critical value. In this case, our critical value, our test statistic, is going to be t, because we are using sample standard deviation. That's when we use t with means. Now with 2 samples, when we find our degrees of freedom, there are 2 things to do. One, if you're doing it by hand, you're just taking the smaller of the 2. So really, whichever sample has the smallest size, you're just going to take the degrees of freedom from that sample. However, if you're using a calculator, you're going to get a completely different value. So be sure you're consistent in your method all the way through the problem so that the grader can tell which one you've used. So the Wade Tract Preserve in Georgia is an old growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is how do the size of longleaf pine trees to the northern and southern halves of the forest compare? To find out, researchers took random samples of 30 trees from each half and measured the diameter at breast height, DBH, in centimeters. Here are the summary statistics and comparative box plots of the data. So based on the graph and numerical summaries, write a few sentences comparing the sizes of longleaf pine trees in the 2 halves of the forest. Well, the shape, the distribution of DBH in the northern sample appears skewed to the right. You see that we have lots of data here, and then it goes out, while the distribution of DBH in southern sample appears skewed left. There are no outliers in either sample. The center, it appears that the trees in the southern half of the forest have a larger diameters. The mean and median DBH for the southern sample are much larger than the corresponding values for the northern sample. Variability, there is more variability in the DBH of the northern longleaf pines. Alright, so construct and interpret a 90% confidence interval for the difference in the mean DBH of longleaf pines in the northern and southern halves of the Wade Tract Preserve. So we're doing a 90% confidence interval for the difference of means, where mu1 is the true mean DBH of all trees in the southern half, and mu sub 2 is for the northern half. So this is a 2 sample t interval for the difference of means. We are given independent random samples of 30 trees from each of the halves of the forest. We can assume that 30 is less than 10% of all the trees in each of those halves of the forest, and both are a large sample. So now actually calculating. So we have our means for each group, our standard deviations for each group, and then also our sample size. Using our calculator, we get an interval 3.9 to 17.724. Also, notice here, degrees of freedom, 55.728. If we were doing this by hand, degrees of freedom would be 30 minus 1, which would be 29. These are quite different. So it's going to be obvious whether you're doing the test by hand, the interval by hand, or using your calculator. So if you were doing this by hand, your degrees of freedom would be 29, and from the table, that would give you a critical value of 1.699. So substituting in all of our values, we get an interval of 3.83 to 17.83. So similar to what you get with a calculator, but just slightly different. So we are 90% confident that the interval from 3.9362 to 17.724 centimeters captures mu sub 1 minus mu sub 2, the difference in the true mean DBH of all southern trees and the true mean DBH of all northern trees. So the formula for two-sample t-interval for the difference of means often leads to calculation errors by students. Also, the interval produced by technology is narrower. So when you're using your calculator, we have a narrower confidence interval than the one calculated using the conservative method, which is going by hand and using your table. As a result, your teacher may recommend using the calculator's two-sample t-interval feature to compute the confidence interval. It does not really matter which one you use, just make sure you're consistent. If you are using your calculator, be sure that you name the procedure, two-sample t-interval, for the difference of means. Then you give the interval and the degrees of freedom.